Welcome students to the homework help video, page 897, 1 through 21 odd and 23 through 31 all. Go ahead and get your books open, your homework out, and let's see if we can't help you with some questions that you've been struggling with here on your homework. The directions for 1 through 21 simply say evaluate. So let's start off with number 1 here. And I think I'm on the wrong page, so if you'll just give me 1 second to actually get my act together here. And here we go. Okay, we're looking at combinations. Remember, that's what this C stands for here. And so whenever you're trying to find a combination, what it means is you have a group of 13 objects, and when you want to know how many sets you can take out of that, sets of 2, and that's what that 2 stands for right there. So first of all, what we do is we pretend we have a permutation problem like that, and then whatever this number is right here, we put it down here in the denominator, and we put it as a factorial, so 2 factorial. Okay, so permutations taken 2 at a time out of a group of 13 would be 13 times 12 over 2 times 1, 2 factorial. We can pretty much do this in our head here. We don't need a calculator. Your 2 would cancel into 12 6 times, and 6 times 13 is 78. So how many sets of 2 could you take out of 13 objects? 78. And remember, combinations do not care about the order. In combinations, if you had a group of the letters A and B, that would be the exact same thing as a group called BA. Order does not matter when you're dealing with combinations. Okay, number 3. Now this is the exact same notation here as this right here. Okay, exact same notation. So we're finding how many sets of 11 objects can we take out of a group that has 13 objects. So up top we would have 13 times 12 times 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 times 3. Okay, that's what this means. Remember, the formula is permutations over, and then whatever this number is right here, 11 factorial. Okay, so all of this would then be over 11 factorial. Now think about it. 11 factorial just means 11 all the way down to 1. So really, I could say 11, 10, 9, 8, 7, 6, 5, 4, 3 cancels out. So 11, 10, 9, 8, 7, 6, 5, 4, 3 cancels out with 11, 10, 9, 8, 7, 6, 5, 4, 3, leaving you with 2 times 1. And then of course, your 2 cancels into 12 6 times, and 13 times 6 is 78. Now if you don't like that, just use your calculator. You can take your calculator and type in 13 times 12 times 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 divided by, and then of course 11 factorial, which we know how to do that on our calculators, and then hit enter. Okay? Alright, moving on to number 5. Well, this would simply mean I want to take sets of 1 out of a group of 7. And so what we do is we first of all write this right here over 1 factorial. Alright, so this one's actually pretty simple. Permutations here for the numerator would be 7 written 1 time over 1 factorial, which is 1, and 7 over 1 is 7. I hope you remember how to do this right here. Maybe you're forgetting. I better review that for a second. If you have something like 5p3, that means you have 5 objects. We'll just say x, we'll use x as 1, 2, 3, 4, 5. There's your 5 objects, and you want to take them in permutations of 3. So you have 5 options to put here, then cross 1 off. You have 4 options to put here, cross 1 off, then 3 options left. 5 times 4 times 3. So here it just simply means that we have 7 objects and we want to pull out 1, so you put 1 blank. How many options do you have to choose from? 7. And so that's why this is 7 up here over 1 factorial. Okay, moving on to number 7. Okay, this is kind of old school here. This is from about 1 or 2 lessons ago, we have a group of 5, and we want to know how many permutations of 3 we can get out of this group of 5. So up top we would have 3 blanks, and the first blank I could put a 5. I have 5 options. After I put something in this blank, I then have 4 options, and after I put something in this blank, I then have 3 options. In the denominator, we would have 3 times 2 times 1. All of these are being multiplied up here. So we can do this in our head. 3 cancels with 3. 2 goes into 2 once, and 2 goes into 4 twice. 5 times 2 times 1 is 10, and 1 times 1 times 1 is 1. So your answer would be 10 for number 7. Okay, number 9, this simply means this right here. And of course, what we're going to do is we're going to take permutations. And so the formula would be this right here over 0 factorial. Now, don't forget that 0 factorial always equals 1. Okay, don't forget that. Now in the numerator, be really careful here. You might think the answer is 0 because you're saying I have a group of 6 objects and I want to know how many permutations of 0 I can take out. Now think about that for a second. If you're taking out 0 permutations, then the only thing you have is just your original group of 6. And so that is why when dealing with permutations, whenever you have a 0 right here, it is understood to be just 1. So 1 over 1 is 1. Okay, and you can just kind of memorize that and remember, just like 0 factorial is always 1. Number 11, well, we have a group of 6, and we're going to take sets of 2 out of it. So we use our formula. Let's draw an arrow and come down this way. Here's my fraction bar. We have a group of 6, and we want to know how many permutations of 2 we can get out of it. So we have 2 blanks here. My first blank has 6 options. My second blank has 5 options. In the denominator, it's 2 times 1. Cross off your 2. 2 goes into 2 once, and 2 goes into 6 3 times. So your answer would be 15 over 1, or just 15. That's actually pretty simple. Now number 13, I want to talk to you about this one, okay? And I really want to help you see this. Now, we already know this right here is going to be 1. Okay, remember we just talked about that 2 problems ago right here when we had a 6 and a 0, but I'll still work it out for you, okay? But what I want to do is I want to work out these 2 together, and I want to show you why. Would you watch this, please? Notice I have 7s going all the way across the top. I have 0, 1, 2, 3, 4, 5, 6, 7 in the bottom, and so that's very important. Let me show you why. We're going to work these 2 out first, okay? So watch what happens. So I have 7 like this, and the other one I have like this. Now I taught you this during the lesson. If this number here matches this number here, and it does, and if this number here plus this number here adds up to these 2 first numbers here that were equal, then these 2 answers will be the same. So I only have to solve one of these, okay, because the other one's going to be the same thing. And so that's why we're kind of doing this one with this one. We're killing 2 birds with 1 stone. Let's go ahead and keep working and see what happens, okay? Now, we just learned a second ago when you have a problem like this with a 0 here, it's going to be 1. Remember, it's like having this right here over 0 factorial, and 0 factorial right here is 1, and this right here is 1, so 1 over 1 is 1. So I'm going to put a little 1 right here and circle it, and I'm going to put a 1 right here and circle it, and cross those off. I'm done with this one, and I'm done with this one. Now, let's go ahead and look at, let's do these 2 now. Let's do this one, and let's do this one, and you're going to see why I'm choosing those 2 in just a second. Look again, I have a 7 here and a 7 here, so those numbers match. And look at the second numbers. When you add them together, they add up to these like numbers, 7. So I'm going to work one of these out. These 2 are equal, so whatever I get for this will also be the answer to this. So I'm really cutting this problem in half. So right here I have 7p1 over 1 factorial, and of course this right here means I'm going to put 1 blank because of the 1 right here, and I have 7 options that go in that blank, so 7 all over 1 factorial. 7 over 1 is 7. So this equals 7 and this equals 7. So I'm going to cross this off and put a 7 right here and circle it. And I'm going to cross this off and put a 7 right here and circle it. Okay, let's continue on. Let's find some more that match so we can cut our time in half. Let's do this one here and this one here. Okay, so I'm going to write this problem. And notice it's going to equal this problem over here because this number matches this number. They're both the same. And when you add these two numbers together right here, they equal those same numbers, that 7 right there. So if I were to solve this, I would have a group of 7 taking out 2 permutations over 2 factorial. Now, of course, this right here, this means I have 2 blanks because of this 2 right here. And then I have 7 options for the first blank times 6 options for the second blank, and then 2 times 1 in the denominator. Cross off your 2, make it a 1. Cross off your 6, make it a 3. 7 times 3 is 21. 1 times 1 is 1. So 21 over 21 is 21. So put a 21 here and a 21 here. And now I've just got 2 left. And that's why it was so important that you saw that when this certain scenario happens, the 2 combination problems are equal, okay? And it saves us a lot of time. So here's my last 2 right here. And actually, I guess technically the 4 should have been right here. And the 3 should be right here. Okay, notice how this first number and this first number both match. And notice how when you add the second number and the second number, they both add up to this first number. And so we know these 2 problems are equal. So I'm going to solve this one. I would have a group of 7 taking out permutations of 3 over 3 factorial. So in the numerator I would have this. Because of this 3, I would put 3 blanks. In my first blank I have 7 options, in my next blank 6, and my next blank 5, all over 3 times 2 times 1. So 2 would cancel into your 6 3 times, and 3 would cancel into 3 1 time. 7 times 1 times 5 is 35. 1 times 1 times 1 is 1. So I have 35 and 35. Now, if you add all of these together, let's see what we come up with real quick, okay? We know we have 1 plus 1, that's 2. We know we have 7 plus 7, that's 14. We know we have 21 plus 21, that's 42. And we know we have 35 plus 35, that's 70. So it looks like we're going to get 128, and that is the correct answer. Okay, let me get a drink of water, and we're going to move on. I don't think I'm going to take the time and use the calculator on this, but it would be worked like this. 52, group of 52, and we're taking out permutations of 4 all over 4 factorial. Now, in the top, because of this 4 right here, I'm going to have 4 blanks. In my first blank, I would have 52 options. In my next blank, 51. In my next blank, 50. In my next blank, 49. Down here, I would have 4 times 3 times 2 times 1. Using your calculator, you could multiply those together and then multiply this together. And I guess if you wanted to quickly reduce some of the numbers, you could say 2 goes into 50 25 times. You could say 3 goes into 51, let's see, 17 times, and 4 goes into 52 13 times. So now your denominator is a 1. You could take 13 times 17 times 25 times 49 all over 1. And if you did that correctly, go ahead and type that in. If you want to check my work, you'll get 270,725. Moving on to number 17. All right, we have 27, a group of 27, and we're taking combinations of 11. So our formula would read group of 27, and we're taking permutations of 11 out of that, all over 11 factorial. So in my numerator up here, I would have 11 blanks. So out of 27 options, then 26, then 25, then 24, then 23, then 22, then 21, and then 20, 19, 18, 17. All over 11 factorial. And let your calculator do the work for you on that one. That's a lot of work. And if you type it in correctly, you will come out with 13,037,895. All right, there we go. Moving on to number 19. Now, number 19, don't panic when you see a variable. It's no big deal. First of all, let's write it the correct way. And then next, let's go ahead and write our formula. Now, we have n objects, now think about that, written in permutations of 1. Well, because of this 1, I put 1 blank, so there's my blank right there. Here's my fraction bar right here. Here's my blank. And in that blank, I have n options, right? Think about it. If this was an 8, I would have 8 options because it was a group of 8. If this was a 9, I would have 9 options for my blank. So because I have n, then I have n options over 1 factorial. All right? So really, it's just n over 1, or n. Let me get a drink of water. You think about that. It's really not too hard. Pretty simple. Okay, let's take a look now at number 21. Number 21. All right, so we have some variables. Did not mean to do that. We have some variables, and that's okay. Let's go ahead and write what we know to write. Okay. Now, I got to be honest with you. To me, it's obvious the answer immediately is 1. And let me show you how. Then I'll go ahead and work it out. I mean, think about it. Let's pretend I had an 8 and an 8 instead of an m and an m. If I have a set of 8, and I want to know how many sets of 8 I can pull out of it, well, I mean, I don't want to say duh, but I mean, think about it. I've got a set of 8, and how many sets of 8 can I pull out of it? 1. I mean, that's all. That's it. Okay, when these two numbers match, it's always going to be 1. But if you want to see it worked out, that's fine. I don't mind doing that. So, first of all, we write our formula. So we have this right here. Now, let's pretend we had an 8 and an 8 here. Okay, in other words, we wanted, think about this, if I had a 8 here and an 8 here, that means I would put 8 blanks, and then I would have 8 options, 7, 6, 5, 4, 3, 2, 1. Let's pretend, let's do a bunch of scenarios. Let's say it was 4 and 4. That means I'd put 4 blanks, and then I would have 4, 3, 2, 1. 4 factorial. Let's say I had 8 and 8. Like this. Well, that means I put 8 blanks, and that would start off with 8 options in 7, 6, 5, 4, 3, 2, 1. So 8 factorial. In other words, what I'm trying to show you is when you have 4 and 4 right here, the answer to this is 4 factorial. And when you have 8 and 8 right there, the answer to that is 8 factorial. So if you have m and m right here, the answer to that is m factorial, and the denominator is m factorial, and anything over itself is just 1. A decently tough problem, not too bad, but you got to think about it, okay? All right, let's take a look now at word problems 23 through 31, and then we'll be finished. I don't think you'll find these too difficult. There are 23 students in a fraternity. How many sets of 4 officers can be selected? Now, on a test or a quiz, you'd have to ask yourself, does order matter? And the answer is no. If I have a group with Caleb, Matthew, and Mr. Earhart in a group, that's the exact same group as Matthew, Caleb, Mr. Earhart, Matthew, Caleb. It doesn't matter what order. A group of 3 people is a group of 3 people as long as they're the same 3 people. So when it asks for how many sets of 4 officers, order doesn't matter, so we're dealing with combinations. So I would write this. I have 23 in my group, and I want to know how many sets of 4 I can pull out. So I would use permutations. I have a 4 right here, so I would have 4 blanks. So 23 for my first, I would have 23 options for my first blank, then 22, then 21, and then 20, all over 4 factorial, 4 times 3 times 2, times 1. I'm going to cross off my 2, make it a 1, and make that an 11. I'm going to cross off my 3, make it a 1, make that a 7. Cross off my 4, make it a 1, make that a 5. And I'm not sure if that helps a whole lot, maybe a little bit, but if I multiply 23 times 11 times 7 times 5, I will come up with this right here, 8,855 different sets of 4 that can be pulled out of a group of 23. All right, and I'm going to grab my calculator really quick and just make sure that that is correct. And that is correct. Okay, moving on to number 24. How many games can be played in a 9-team sports league if each team plays all other teams once? So if you think about it, look, if you have America versus Brazil in soccer, okay, isn't that the exact same thing as Brazil versus America? Of course it is. In other words, order doesn't matter. So if order doesn't matter, then we're dealing with combinations. So we have a group of 9 teams, and we want to see how many sets of 2 we can pull out. Why sets of 2, Mr. Earhart? Well, it's very obvious, because how many teams do you need to play a game? 2. So you've got to pull out sets of 2. And so, of course, my formula would be permutations of 2 all over 2 factorial. And so this 2 right here means I have 2 blanks. And so in my first blank I would put a 9, and in my second blank an 8, all over 2 factorial. That's 2 times 1. Cross off your 2, make it a 1, cross off your 8, make it a 4, and the answer is 36. Now, if each team plays each team one time, there's going to be 36 games. What if we wanted to double that and each team play each team twice? Well, guys, that's what it says right here. Well, guys, that's just pretty much common sense. It doubles. So if that happens, there's really no need to use combinations and work all that out. If each team played each team once, that's 36 games. If each team played each team twice, that would be 72 games. You just double the 36. Moving on to 25. On a test, a student is to select 10 out of 13 questions. In how many ways can this be done? Now look, if you're choosing 10 questions, it doesn't matter what order they're in. The 10 questions you choose are the 10 questions you choose. So order doesn't matter, so we are dealing with combinations. So we have a group of 13, and we want to know how many sets of 10 we can pull out. So we use our formula. And then because of this 10 here, I'm going to have 10 blanks. So it'd be 13 options, then 12, then 11, then 10, then 9, then 8, then 7, then 6, then 5, then 4. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All over. Now think about this, guys. 10 factorial. That would be 10 times 9 times 8 all the way down to 1. So I'm going to cross off my 10 times 9 times 8 times 7 times 6 times 5 times 4 and leave my 3 times 2 times 1 and cross these off here. I'm going to cross off a 3, make it a 1, make my 12 a 4, and then basically we would have, I'm not sure exactly, 1, 1, 3, 1, 3, 1, 3, I think 143 times 4 over 2. But if you typed all this into your calculator, I was trying to do it in my head, and I'm not going to be able to do it, but if you type this into your calculator, 13 times 4 times 11 divided by or over 2 times 1, you will get 286. So, how many different sets of 10 can I take out of a group of 13? 286. Let me get a drink of water here and we'll take a look at number 26. 26 is so large, they do not want you to have a number answer, and I wish they would have told you that. I looked in the teacher's edition here, and you're going to see it's just really a lot of really big numbers, so we're not going to work all of this out. We're just going to set it up, and I wish they would have told you that in the problem. But suppose the Senate consists of 58 Republicans and 42 Democrats. How many committees can be formed consisting of 6 Republicans and 4 Democrats? Okay, well, let's start off first of all noting that we have a group of 58 Republicans. And out of that group of 58, we want to pull out sets of six Republicans. Now the other combination we're looking at is we have a group of 42 Democrats, and we want to pull out sets of four. We want 4 Democrats. And I taught you this during your homework. You do multiply these together when you're dealing with different combination problems like this, getting one big group. Now, obviously, that's as far as I want you to go. We're not going to work all that out, and I wish they would have told you that in the original problem. That's the answer they have in the teacher's edition, and that's good enough for me. The answers would be huge, but that is how you would set it up, and that's sufficient for this problem. Number 27, of the first 10 questions on the test, a student must answer 7. Of the second 5 questions, a student must answer 3. And how many ways can this be done? Well, if you think about that, the first 10 questions, that's a group of 10, you must answer 7. And order doesn't matter. Any 7 questions you ask, no matter what order they're in, they're still the same 7 questions. And then we have a group of 5 questions, so I'm going to put a 5 right here, and you must answer 3. So we're pulling out 3 sets. Okay, now let's go ahead and work with this one first. We would have permutations of 7 over 7 factorial times, here we would have permutations of 3 out of a group of 5 over 3 factorial. Now I'm going to grab my calculator real quick. To be honest with you, for this problem right here, we would have 7 blanks because of this 7 right here. So 10 times 9 times 8 all the way down to, I think, let's see, it should go all the way down to 3, all the way down to 4. So times 8, 7, 6, 5, 4, all the way down to 4, all over 7 factorial. Okay, all of this right here goes to this first fraction right here. Okay, and then times, now the numerator right here, we'd have a group, we would have 3 blanks, and we start with 5, so we would have 5, 4, 5 times 4 times 3 over 3 factorial. Alright, so I'm going to grab my calculator real quick and work on this first fraction. 10 times 9 times 8 times 7 times 6 times 5 times 4 divided by 7 factorial, and I'm getting 120. Now the second fraction, we could probably do it faster in our head. 3 factorial is 3 times 2 times 1. Cross off your 3's, cross off your 2, make this a 2, and you get 5 times 2 times 1 is 10 over 1, so 10. So 120 times 10 would be 1,200. So that's how many different combinations you could get out of choosing these sets of questions on this test. Number 28, lines and triangles form from points. Let me get a quick drink here while we look at this. There's 2 questions here. Let's focus on the first question first. How many lines are determined by 8 points? No 3 of which are collinear. So the best way to get points that are not collinear, that have no 3 points collinear, is kind of draw them in a circle like this. 1, and then 2, and then 3, and then 4, and then 5, 6, 7, and then 8. Of course, that there looks like they're really close to being 3 points collinear. We'll bring that out a little bit, and bring that one down a little bit, and that one down, and that one out. That should do it. That looks pretty good. Okay, so let's look again at what it's asking. How many lines are determined by 8 points? Out of these 8 points, no 3 can be collinear. Well, this is fine. No 3 points line up in a straight line. Now 2 points do, but remember, any 2 points you draw anywhere are always going to line up in a straight line, always, okay? But no 3 points are in a straight line here, so we've done pretty well. And here's what they're asking. How many lines are determined by these 8 points? Now come on guys, think about it. How many lines? Let me ask you a question. We could do this. We could do this, and then this, and then this, and then this, this, and this. And then come over here and draw this one, and 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 this one. Then jump to this, and keep track. And I should have started keeping track earlier. That's going to be really messy, and there's just no need to do that. I mean, here's what we're doing. Look at this. We have how many total points? 8, and we want to take them in sets of how many? 2. Mr. Earhart, why 2? Because in order to draw a line, you need 2 points. And no 3 points are collinear, so you know it's going to be in sets of 2. So all that I want to know is how many sets of 2 I can get out of all 8 of these points. And so it would just simply be my good old formula, permutations of 2 out of sets of 8 over 2 factorial. So my numerator would have 2 blanks. In my first blank I would have 8 options. In my second blank 7, all over 2 times 1. Cross off your 2, cross off your 8, and your answer would be 28. So how many lines can be determined by 8 points as long as no 3 are collinear? 28. 28. Now, the next question says how many triangles are determined by the same points. Now come on, I didn't mean to unveil the answer there, but come on, this isn't hard. How many triangles? Well, how many points do you need for a triangle? Don't you need 3? So you could start here and say, okay, here's 3 points, and then here's 3 points, and then here's 3 points. It's going to be hard. And then here's 3 points. That's going to be hard. And then next you jump over to this one and go to this one. It's just going to be really hard. So let's do it a fast way using a formula. Look, you have how many total points? 8. And you want to know how many triangles are determined by the same points. Well, triangles have to come in sets of 3. You have to have 3 points to draw a triangle. So I want to know, I'm not sure why I put a P there, it should be a C. I want to know how many sets of 3 I can take out of 8 objects. So our formula is 8 permutations of 3 over 3 factorial. So my numerator, because of this 3 right here, I'm going to have 3 blanks or 3 numbers, 8 options, then 7, then 6, all over 3 factorial, so 3 times 2 times 1. Cross off your 2, cross off your 6, cross off your 3, cross off your 3. 8 times 7 times 1 is 56. 1 times 1 times 1 is 1. So there are 56 unique triangles you can draw from these 8 points. Pretty interesting how these formulas really help, okay? All right, number 29. I'm not a poker player at all, so understand that, but we can still use the problem. How many 5-card poker hands are possible with a 52-card deck? Well, look, I don't care if you've got 5 cards in your hands that are 1, 2, 3, 4, and 5. If you shuffle that hand and now the order is 5, 3, 4, 2, 1, it's still the same hand, so order does not matter. So we have a deck of 52 cards, and I want to know how many sets I can get, how many sets of 5 I can pull out of that. So I would have this right here, permutations of 5 out of a total of 52, all over 5 factorial. And of course in the numerator we would have 5 numbers because of this 5 right here, so I would have 52 options, and then 51, and then 50, and then 49, and then 48, all over 5 factorial. I'm not going to take time and type that in, but I will give you the answer so you can practice. If you do type that in correctly, you're going to get 2,598,960. And that is the correct answer. All right, number 30. How many 13-card bridge hands are possible? Well, it would be, I have a total of 52, and I want to take out of that 52 sets of 13. So basically what I have would be 52 permutations of 13 all over 13 factorial. Now I don't think we're going to write all of this out. Sorry for yawning, I apologize. I don't think I'm going to write all of this out, but you know in the numerator it would be, you would have 13 numbers up top because of this 13, and your first option would be 52, and then 51, and then 50, and you keep going down 49, 48, 47, 46, all the way down to, I believe, 40, I believe is where you would stop. So 52 times 51 times 50 times 49 times 40, 8 times 47, all the way down to 40. I'm just going to put dot, 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 all the way down to times 40, all over 13 factorial. Now I'm not going to take time and type that in my calculator. Please feel free to do it yourself so you can practice and make sure you're doing it correctly. But if you did that correctly, you will get 635 billion 13,559,600. Okay, so there we go. This is good practice, practical word problems on what we've learned. Now, number 31 has 3 parts to it. Bert, we've all heard of Baskin and Robbins ice cream. Let me get a drink of water here. Bert Baskin and Irv Robbins began making ice cream in 1945. Initially, they developed 31 flavors, one for each day of the month. Question number 1. How many 2-dip cones are possible using the 31 original flavors? Now listen, if order of flavors is to be considered, so we are worried about order, and no flavor is repeated, so no repeats. So now think about that. That's permutations, guys. That's permutations, because it says order, let's see, order is to be considered, so order is important. So we have 31 objects, 31 original flavors, and we want to find permutations of 2. Now I put a P here instead of C because we're not dealing with combinations, we're dealing with permutations. And how did I know that? Well, for the third time, because it says order is to be considered. Now it also says no flavor is repeated, so because of this 2 here, I put 2 blanks, and because no flavor is repeated, for my first blank I had 31 options. Then when I put one of those flavors here, I'm left with 30 options. So if you multiply those 2 together, 30 times 31, you will get 930. 930 for question A. Now let's move on and take a look at question B. How many 2-dip cones are possible if order is considered? So that's permutation, and flavor can be repeated. So I better be careful putting a P here. Now flavors can be repeated. So really, it's still 2-dip cones, so I have 2 blanks. And my first blank, now watch this, my first blank I have 31 options, but repetition is allowed. So in this blank I have 31 options again, because it doesn't matter if I put a chocolate scoop in, I could also put chocolate over here. So in other words, if I had 31 options for the first blank, even though I put chocolate here, I still have 31 options for the second blank. 31 times 31 is going to give you 961. And now let's take a look at letter C. How many 2-dip cones are possible? Look at this. If order is not considered, so order doesn't matter, and no flavor is repeated. So no flavor is repeated, okay? So I'm going to be doing combinations. I have a group of 31 flavors, and I want to find out how many sets of 2 I can pull out of that group of 31. Well, we know how to do it. It's going to be permutations of 2 out of group of 31 over 2 factorial. So I know up top right here, because of this 2, I'm going to have 31 times 30, and in the denominator it will be 2 factorial, or 2 times 1. Now 31 times 30 is 930 over 2, and so the answer is going to be 465. 930 divided by 2 is 465. That's the different combinations you can get out of 31 flavors in sets of 2. Okay, I hope this homework help video has been a help to you. Call or email if you have any questions, and I hope you have a good day.